Hello, I'm Keith Graham from Codasip. I want to introduce you to a topic that actually came to our mind back in May when I was at an open source conference where 7 different companies that supported RISC-V, and we were all addressing the question is we need more processor engineers. And the best place to get these engineers is actually the software engineer. So let me go into my presentation here. So first of all, what do processor engineers do? Right? Let's take a look at making the impossible possible. First of all, I might have a particular design where at a technology node, and I can't get the number of cycles that I need at a technology node. So I got to figure out how do I improve or enhance the efficiency of the core that I have. Another thing might be that my core consumes too much energy. So I need to figure out how to optimize the resources of my core to match the actual application. Also, processor engineers take a look at the core is too large. It's too expensive. How do I make a small core perform like a large core? Right? These are different questions that processor engineers need to address or do address. Or it might be something that the resource isn't in any core, and I need to actually expand my market by actually bringing a new resource and actually changing what a processor actually is performing. So let's take a look at how a software engineer can actually help address these questions. But first of all, when I taught at the University of Colorado, I always like to ask questions to my class. So I'm going to ask you some questions. So the first question here is, can you name some good software practices?
Separation of concerns.
Separation of concerns.
Testing,
Testing. I'm big in test-driven development, unit tests. I'm really big on that. Don't repeat yourself. To me, is function calls, right? Anything else? Well, take a look at it. I think some of these things is what we just got back as answers, right? Use of functions, modularity, encapsulations, compiler directives, use of defines, use of macros, and I should have put unit tests, right? That's a very important thing. And so when we take a look at those good practices, if we're going to ask software engineers to become good processor engineers, right, we actually have to enable the software engineers to implement or become the processor engineers using the best practices of software engineering, right? We don't want to take all the good skills that they've learned from software engineer and teach them another set of skills. We want to actually take the best practices and map that into processor engineering. Now, let's take a look at function calls. Well, function calls increase productivity, right? I designed something through a common function. As you said before, I'm not going to repeat myself. I'm going to do it once. I'm going to use a unit test, validate that the function works, and verify it. That means anytime I call that function, I know it works because I've already validated it through unit testing. Now, so a single instantiation of hardware means I reduce the amount of hardware I designed, right? You know, I'm not going to write the same function in software multiple times because if I do that, it's prone for errors, right? And I also potentially could explode my code size, right? In our tool here, which we'll talk about in a few minutes here, you can actually say inline function, which means then it would actually implement it as many times as you use it, just like an inline code in regular software programming. So once again, if you verify it once, you mitigate risk, right? Because I validated it once. And I can use it wherever I want to. And if you notice here, the way I implement my new instructions, I think it's very much like an embedded software. I used to teach embedded software as well. You can see I have what we call hcodal, which is a header file. Then I have codal, which is really like a C file. I create my own little library of functions. And I also, if I want, I can create aliases that make it simpler for programming. Now let's go into looking at defines and macros, right? You use those in at least embedded software. I'm assuming you use that in other software as well. So header files define constants and macros. Very similar to functions. I'm creating abstractions. If abstraction increases efficiency, increases productivity, but more importantly, it reduces errors. So you can see here in this set of code that I've did a screenshot. I have my .h codal, which is like my header file, and it's very much like you might have in a standard preprocessor. We use macro preprocessor instead of a C preprocessor. Now, we also further want to abstract the actual microarchitecture, right? A software engineer might not understand pipe stages or the machine language bit codes, so we want to actually even abstract further from that. So you can see from the way this is written, we are just going to create encodings. We're going to define, for example, the MAC operation, and the multiply, subtract, accumulate as well. We're going to assign it to a module. And then we're going to say that we have a MAC operation that has 3 source registers and 1 destination register. And the software will actually create the opcode for you, right? You do not even need to know RISC-V code. It will generate a opcode out of the custom opcode space of RISC-V and assign one for that instruction. And to actually access it, all you need to do is say git encoding for the instruction that you just created. So the software engineer never needs to know the opcode in this software. They just need to look at a higher level or an abstracted view of the instruction. So once again, abstraction improves efficiency, productivity, and reduces errors. Now, I'm going to ask some more questions now. Now let's take a look at who develops a sensor who develops a sensor signal conditioning function? Who develops it? Is it the digital software designer, signal processor engineer, or is it the processor engineer? Question, which one? Both. I'm going to say it's normally probably the signal software engineer is going to be the one who's going to create that function, right? Because they are the one that knows, you know, how butterfly works in an FFT or FIR filter, for example. Now, who develops hearing aid functions or the algorithms? Let's talk about algorithms. Maybe get rid of the word function, algorithms. So who develops the algorithms for a hearing aid? Software engineer, right? Or a signal processing engineer who might be even more abstracted, but it's a software engineer or the processor engineer. Who develops an automotive crash avoidance algorithm? Is it the system and control programmer or the processor engineer? Right? It's the system and control programmer. Who develops the artificial intelligence algorithm? Is it the AI software engineer or the processor engineer? Yeah, I know I'm giving you a lot of leading questions, right? But if we look at it, it is always the person writing the algorithm, right? So if you think of it, the person who writes the algorithm, at least from my imagination, would be the best ones to be able to accelerate or change my core or update my processor to optimize for that type of function. Now, domain-specific or function acceleration relies on optimizing one or more software algorithms by the experts. And we just sort of answered the question that the experts are the people that are programming or writing those algorithms. Now, this was something we showed off at EU RISC-V Summit, but it is just an example of what we did. So last January, we started a project at Codasip in labs where we're taking audio data in, transforming it, and doing an AI for anomaly detection. So we could actually detect early that a fan was failing before you could before a person could actually hear the fan go bad or it became critically and failed. And so, but we had some constraints on the problem where we had to be at below 40 megahertz at 40 nanometers because that matched the technology node we were looking at. But in reality, our first estimates of the code before we accelerated it would be more than 80 million cycles. So we had a mismatch there. So front end performs the conditioning FFTs. So we must accelerate the digital signal processing, but then we also must accelerate the AI. So you can see we have a signal processor engineer working on this problem and an AI engineer working on this problem. Now let's take a look at the DSP signal conditioning engineer. So when he defined the MAC operation for the coding, it has many things it has to do, right? This is exactly what he wants the MAC to do. It has to do the multiply, we have to round, we have to, the middle section, decide whether I'm doing the add MAC or the subtract MAC. I got to do a saturation check, and then if I have to saturate, I have to create a saturated result. So this is exactly what the signal processor engineer requires. We actually wrote that down, and if you think of it, it's just the flow that I would write a software program. And this is what he created to create a new instruction. To me, this looks very much like a C program. So we're modeling very much like a software engineer and not a processor engineer. You notice there's nothing about decodes, there's nothing about opcodes or pipeline registers. Now, by doing this and several other operations, we improved over 10x the performance over the standard C operation. Now, but let's take a look at, I can create these new instructions, but I also have to use these instructions and make it easy for the software. So good software practices is libraries, right? Utilizes libraries for optimization, right? Because if I have a library, the nice thing about libraries actually abstract the hardware, the core, from the software algorithm. So that I could write an algorithm that might run on one core that doesn't have the acceleration. It will be slower because it's just using standard C code, but if I have a core that has the accelerated code, it would actually be accelerated. So software libraries are good practices for acceleration. Now, if we look at this example here, ARM uses CMSys libraries for abstraction already. If you compile using CMSys DSP for an FFT, if I have an M4F or M7F, it's going to use the ARM DSP math portion of that library. If I have an M0 plus or an M4 or M7 that doesn't have that, it just uses C code. Same thing here. So as we create these new instructions, we were going to utilize them in libraries, because this way we can guarantee that any third party that uses a standard library will realize the work that you've just done in these accelerated algorithms, or also you can actually access these new instructions directly if you own the code as well. Now, another way of taking a look at it, in our example, we have an anomaly detection software. We had a library that we go up to the top. We actually just ran this on RISC-V core, but same thing. We did a switch in the compile and said we don't have the acceleration. So it goes to the top. We just use standard C libraries, and then we actually then have a switch that said, okay, let's compile the code saying that I do have the acceleration, and I go to the bottom, and all of a sudden I have my enhanced core with the DSP operations and neural network operations, and utilizes the C code. Same exact software algorithm, exact same software program, and it was just got the benefits of the new instructions through the use of a different set of the libraries. So let's take a look at a little bit more about how it's important for software engineering to be the new processor engineer. So our AI engineer first developed this, what I call an AI MAC operation. So we can do this in a single operation. So the data has been quantized to 8 bits. We're doing 4 8-bit multiplications, and then we're accumulating. So this is actually going to enhance our operation. Thank you for coming back after that interruption, but just wanted to get back to an example where our AI engineer actually created this new instruction because he understood the algorithm. And so we actually have this special MAC operation for AI where we did quantized, the data was quantized to 8 bits. So we did 4 multiplies and accumulate in one single clock cycle. Now, what that really resulted in was this next piece of two instructions. We had these special load word unaligned data for the general matrix multiplication loop. And you can see how tight that loop is. It's only 4 instructions. But we actually are doing 4 mat-mul operations in 4 cycles. So we're actually doing 1 mat-mul for every cycle. We actually know how, without any new instructions, but just rewriting the general loop, where we can actually expand that to 8 mat-moles, or actually 2 mat-moles per clock cycle. And when we get to that point, from looking at data, we have a core that's basically the size of an M0 plus that's twice as fast in doing neural network math than the M7. Once again, this is the power of a software engineer becoming a processor engineer. And so you can see the net effect at the high-level application layer that we've actually enhanced the performance of the application by over 4x. But more importantly, we actually decreased power by over 6x. So this is just an example of a software engineer taking the knowledge of their algorithms, and they are implementing the new instructions through a format that looks very much like a software programmer's, and seeing multiples performance as increase in performance as well as reduction in power. So the RISC-V ecosystem has enabled the software engineer to become the new processor engineer. So thank you very much for everyone.
Give him a big hand.
Yeah.